Captions in English, please. So this is the 8th video on chapter 2, and it's on temperature. So if you put a pot of water on the stove and heat it, the temperature will rise, correct? So you may think more heat means more temperature. And heat and temperature are the same thing. Well, that's incorrect. Don't think like that. Heat and temperature are not the same. Atoms and particles in a substance do not always move at the same speed. Within a sample, you may have particles that move more or less. So there is a range of energy of motion, and the energy of motion of the particles is called kinetic energy. The kinetic energy is the energy of motion of the particles. And not all particles within a sample have the same kinetic energy. So temperature is a measure of the average kinetic energy, the energy of motion of the molecules in a substance. So it represents the average of the, the measure of the kinetic energy of all the molecules in the substance. So it is not energy. Temperature is not an energy. And so it represents the average kinetic energy. And so the higher the temperature, the larger the kinetic energy of the molecules. Temperature does not depend on the amount of the substance. For example, here you have a tea kettle at 100 degrees Celsius and a tea cup filled with tea at 100 degrees Celsius as well. Both objects are at the same temperature, right? So it depend on the fact that there is more or less water at 100 degrees Celsius, for example. Heat, on the other hand, is the exchange of thermal energy between samples of matter. So it's when energy is transferred. Because heat will flow from the matter that has high thermal energy to matter that has a low thermal energy. So always from high thermal energy to low thermal energy, until they both reach the same temperature, until both samples reach the same temperature. So heat is exchanged through molecular collisions between the two samples, right? Because molecules are vibrating or moving around. Those collisions, allow the heat to be flowing from the high thermal energy to the low thermal energy sample. And so the quantity of heat depends on the amount of the substance and what it is made of. So here we still have our kettle and a teacup with the same water at 100 degrees Celsius. However, the tea kettle with more water contains more heat than the smaller teacup. To visualize this, imagine you would get this burning water on yourself. You would get burned much more by all the water from the teacup than the tea kettle, than the teacup. The teacup, it's a smaller amount, and so there would be less exchange of heat, from the boiling water to your skin than from the water from the tea kettle. So heat depends on the amount of the substance and what is it made of also. So there are 3 temperature scales that you need to be aware of. The first one is the Fahrenheit. The Fahrenheit temperature scale is based on a scale proposed in 1724 by the physicist Daniel Gabriel Fahrenheit, that was born in 1686 and died in 1736. So Fahrenheit's original scale used 3 reference points. The freezing point of brine. Brine is concentrated salt water. He considered this was the 0 degrees Fahrenheit. Ice water, which was 32 degrees Fahrenheit. And then the human body temperature, blood heat, was considered 96 degrees Fahrenheit. So this scale was later recalibrated recalibrated so that the freezing of water into ice is exactly 32 degrees, while the boiling point of water is exactly 212 degrees. So it's using now a boiling point of pure water and a freezing point of pure water. And so because of that, the human body temperature is normally 98.6 degrees Fahrenheit for a normal body temperature. The second temperature scale is the Celsius. It's based on a scale that was established by a Swedish astronomer Anders Celsius, who was born in 1701 and died in 1744. So from 1743 until 1954, the degree Celsius was defined as the freezing point of water, and 100 degrees Celsius was defined as the boiling point of water. Today, the Celsius scale is defined by two different temperatures. The absolute zero, which is a negative 273.15 degrees Celsius, and the triple point of water, which is 0.01 degrees Celsius. The triple point of water, what is it? It's the temperature where water coexists as all three states of matter. So it can be a solid, a liquid, and a gas simultaneously at a certain temperature. And so here, basically, it's almost 0 degrees Celsius, 0.01 degrees Celsius. It's a temperature where water can coexist in all three states. So that's the Celsius scale. And then the last scale is the Kelvin scale. So the Kelvin temperature scale is named after the Belfast-born Glasgow University engineer and physicist William Thomson, who is also known as being the first Baron Kelvin. So born in 1824 and died in 1907. And he wrote about the need for an absolute thermometric scale. So he defined the absolute zero, which is the lowest temperature possible at which matter reaches minimum entropy. And he defined it as being precisely 0 Kelvin. So what is the entropy? Entropy is a measure of the system's energy that is not available to work. So in a system, you have energy, and there is part of the energy that you cannot use to do work, meaning, that can be used to do something else that can be transferred to do something useful. Entropy is this part of the energy that is not available for that and that you cannot use. So in January 2013, physicists announced that they had created a quantum gas made up of potassium atoms with sub-absolute zero temperatures. So only a few billions below, so which means 0 point and then maybe 8 or 9 zeros and then a digit, right? So it's almost a 0 Kelvin, but a few billions below. So sorry, it should be negative 0 0.8 zeros and then a digit. So it doesn't mean that the atoms are colder than 0, but it is negative by definition because the entropy doesn't follow the normal trend. So until the 0 Kelvin, the entropy has a normal trend, but then below that it's not behaving the same way. So this absolute scale, the Kelvin scale, really represents the movement of the molecules, really represents the average kinetic energy of matter. So that's the one you will use for calculations that involve temperatures. So there are, this summarizes the three scales that are used for measuring temperature. You can see that they are both showing you here, or all three showing you the same freezing point of water. And so depending on the scale, it's a different temperature. 0 degrees Celsius for the Celsius, 273 Kelvin for the Kelvin, and then 32 degrees Fahrenheit in Fahrenheit. So that's the freezing point of water. And then the boiling point of water is 100 degrees Celsius or 373 Kelvin or 212 degrees Fahrenheit. So you can see that the difference between the freezing and the boiling point of water is exactly 100 degrees Celsius in the Celsius scale, or 100 kelvins in the Kelvin scale, but 180 degrees Fahrenheit in the Fahrenheit scale. So the Fahrenheit scale has smaller units, so you need more of them for that same difference in temperature. And so it's not showing here on the scales, but the lowest temperature in the Celsius scale would be negative 273 degrees Celsius. In the Fahrenheit scale, it's negative 460 degrees Fahrenheit. And in the Kelvin scale, it's the absolute zero, 0 Kelvin. So the Kelvin scale cannot have negative numbers. It's always positive values because it's meant to really represent the average kinetic energy of the substances. So an energy can only be positive. So what are the equations that allow you to change between degrees Fahrenheit and degrees Celsius? So the equation is degree Celsius equals degree Fahrenheit minus 32 over 1.80. And so this comes from the fact that a degree Celsius is 1.8 times larger than a degree Fahrenheit, right? So when you're moving up by 1 degree in the Celsius scale, you've moved up by 1.8 in the Fahrenheit scale. So that's why there is that 1.80 in the denominator. And the standard used for the 0 degree on the Fahrenheit scale is lower. It's a lower temperature than the standard used for the 0 degree in the Celsius scale. And so this explains the degrees Fahrenheit minus 32, because if you have 0 degrees Celsius, that means your degrees Fahrenheit must be 32. So 32 minus 32 would be 0 degrees Celsius. So the degree Celsius 0 is in Fahrenheit 32 degrees. And then if you have 0 degrees Fahrenheit, then you have negative 32 over 1.8, and this comes up to about negative 18 degrees Celsius for the 0 degrees Fahrenheit. Now the equation to convert kelvins to Celsius, it's that kelvins are equal to Celsius plus 273. So we've noticed that the size of a degree on the Kelvin scale is the same as on the Celsius scale. And, you know, the Kelvin scale was established from the Celsius scale. So they kept this degrees size of the degree the same. It's simply offset by 273. And even though the Kelvin scale was based on the Celsius scale, we do not call the divisions on the Kelvin scale degrees. There is no degree symbol in front of the capital K. We just call them kelvins. And so if the kelvins are the same size of the degree Celsius, then that makes 1 Kelvin 1.8 times larger than 1 degree Fahrenheit. And so the 0 standard on the Kelvin scale is a much lower temperature than on the Celsius scales. And we've seen how, you know, 0 Kelvin means it's negative 273 Celsius, right? So it's a much, much lower temperature when you have a 0 Kelvin versus a 0 degree Celsius. So this summarizes all the kinds of equations you may need to convert between the different temperature scales. So on top here, we have the conversions between Celsius and Kelvin. And below it's between Celsius and degrees Fahrenheit. So notice how there is no equation between Fahrenheit and Kelvin. You have to go through the degrees Celsius to change degrees Fahrenheit into kelvins, or vice versa. To change kelvins to degrees Fahrenheit, you need to change first the kelvins into degrees Celsius and then Fahrenheit. So let's go through an example on how to convert temperatures. So Ray Bradbury wrote a book called Fahrenheit 451. What is this temperature in degrees Celsius? So you want to use the same process as when you're solving problems with regular unit conversions. So first thing, you want to extract, from the text what the question is asking for. And here it's asking to convert 451 degrees Fahrenheit into degrees Celsius. The given amount is 451 degrees Fahrenheit. So we need to find an equation that relates degrees Fahrenheit to degrees Celsius. So which conversion equation to use? So you want to use the ones that have degrees Fahrenheit and degrees Celsius in it. And there's two of them. Degrees Celsius equals degrees Fahrenheit minus 32 over 1.80, or degrees Fahrenheit equals 1.80 times the degrees Celsius plus 32. So here we start with degrees Fahrenheit. We want to be able to plug in the degrees Fahrenheit and calculate degrees Celsius. So we want the equation that solves for the degrees Celsius. And so that's going to be the first one. The one that has degrees Celsius isolated equals an equation that has degrees Fahrenheit in it. So the final step is to plug in the values. So here, the degrees Fahrenheit are 451. So you have 451 minus 32 in the numerator divided by 1.80. 232.77, etc. That's the calculator answer, right? And here you have to be very careful how you use the calculator. If you do 451 minus 32 divided by 1.80, your calculator will follow the PEMDAS rule and will do the division of 32 divided by 1.80 before it does the subtraction. So it would basically it would do 451 minus, and it would do this intermediate calculation of 32 divided by 1.80 before it subtract that to 451, which would lead to a wrong answer. So be very careful. You need parentheses in the numerator. So 451 minus 32 in parentheses divided by 1.80. You want the subtraction to be done before you divide the intermediate answer of the subtraction by 1.80. So the temperature that was given to the ones place, right? It was to the degree. And so we want to keep the same precision here and give the final temperature in Celsius to the degree, to the ones place. So 232.777 will be rounded to 233. The 2 will be rounded up to a 3, and that's then rounded to the ones place, and that's the temperature in degrees Celsius. Let's go through another example. The surface temperature of the sun is approximately 5,505 degrees Celsius. What is this temperature in Kelvin? So what is the question asking for? Here it's asking for a temperature in Kelvin, and we're given a temperature in Celsius. So that means we need to convert 5,505 degrees Celsius into kelvins. The given is the 5,505 degrees Celsius. So we will need the equations between degrees Celsius and Kelvin. So which conversion equation to use? We have temperature in degrees Celsius equals temperature in Kelvin minus 273, or temperature in Kelvin is the temperature in degrees Celsius plus 273. So out of those two, you want to use the equation that has degrees Kelvin isolated, you know, it should be solving for temperature in Kelvin and have the degree Celsius in the formula. So that means you need the second equation here. Temperature in Kelvin is the temperature in degrees Celsius plus 273. So now we are ready to calculate and we need to plug in the values. The temperature in degrees Celsius is 5,505 plus 273. The calculator answer is 5,778 kelvins. We don't say degree for kelvins, we just say kelvins. So is it rounded properly? So if we look at the given temperature, it's given to the ones place. And so we want to keep the kelvins in the end to the ones place. And so they are already rounded to the ones place. So we'll keep it like this. So that's the final answer, 5,778 Kelvin. Let's do a final concept check. And this time I want you to pause the video and try to solve this problem before you watch the answer. It is important you try before you watch the answer. So the normal body temperature for a dog is approximately 102 degrees Fahrenheit. What is this equivalent to on the Kelvin temperature scale? So the first thing you want to ask yourself is, you know, what is the problem asking for? So it looks like we need to convert into Kelvin and that we have 102 degrees Fahrenheit to convert into Kelvin. So the given is 102 degrees Fahrenheit. And we need to convert that into Kelvin. So we need an equation between Fahrenheit and Kelvin. Is there a direct conversion factor, a conversion equation for degrees Fahrenheit to Kelvin? No, we don't. We saw that we only have degrees Fahrenheit to degrees Celsius, and then degrees Celsius to Kelvins. So we will have to do two conversions, two separate conversions here. And the equations for converting degrees Fahrenheit to degrees Celsius, there are two of them, this one or that one. And for converting degrees Celsius to kelvins, we have also two equations, these two. So because the given amount here is in degrees Fahrenheit, so we are looking for degrees Celsius at first. So you want to find the equation that solves for degrees Celsius and where you can plug in degrees Fahrenheit. So it's going to be the first equation here that says degrees Celsius equals degrees Fahrenheit minus 32 over 1.80. Once we have our degrees Celsius as an intermediate answer, we want to convert them to degrees Fahrenheit to kelvins. And so we will use the equation that solves for kelvins and that has degrees Celsius, you know, that you can plug in into the formula. So that's the second formula here that you need to use for the second conversion. Now we are ready to calculate and plug in the values. So let's start with calculating the degrees Celsius. You take degrees Celsius equals degrees Fahrenheit, and here it's 102 minus 32 divided by 1.80. In the calculator, make sure you do the subtraction before you divide by 1.80, which means you do 102 minus 32 equals, or you do open parentheses 102 minus 32 close parentheses. Then divide by 1.80. Make sure you have the subtraction done before you divide. If you simply type 102 minus 32 divided by 1.80, the calculator will divide 32 by 1.80 and take that intermediate answer and subtract it to 102. And this would lead to a wrong answer. So you should get 38.8888 degrees Celsius. This is an intermediate answer, so we do not round. Next, you want to calculate the kelvins from that. And so you take your degrees Celsius and you add 273. So 38.888 plus 273, the calculator answer is 311.888 kelvins. So to find out how you run this in the end, you need to look at the given temperature. This was given to the ones place, to the degree. So you want to round in the end to the degree, to the ones place. And so here, the ones place has a 1. What comes after is a 8. So you need to round up. So the 1 will become a 2 in the ones place. So that's going to be rounded as 312 Kelvin. So that it's to the ones place or to the degree. We want to keep the same precision for the final temperature as the initial temperature.